Okay. So we start from where we stopped last time. To recall, we are considering joint random variables. Now suppose it is basically nothing but what I am doing. What I am doing is nothing but generalization of the one variable case to two variable case. So I have certainty, that is 1 also. Probability of that is 1. Okay, involving two variables now. Now, like earlier, like the case of single random variable. Now, for the joint case also, we can assume that we are given a function f of the two random variables x comma y. That is, every time I observe x and y, say temperature and humidity, this function, in this function I plug in those values, I get something. Next time again I conduct the experiment, I plug in the value of temperature, humidity, that is x and y, I get another value, and so on and so forth, which means the function also is random. So, if so, what is its average value? So, what I will do, I will multiply by the chance factor, that is, if capital f x comma y, I will assume when it is within this box, its value does not change because the widths are infinitely small. So, its value will be same as its value at the corner, that is f of small x comma y, all right. So, that value, but it is not guaranteed that I will get that value always. So, I have to multiply by its chance. Chance is chance of capital X and Y falling here. So, I multiply by the chance. Again the same thing I do on another box, on another box, on another box. So, I go on adding. Okay. So, basically multiplying this by a weight. So, I get a weighted sum. So, I will have the weighted average. Weighted average will be, if I go to the next page, will be f of this value you are multiplying by the chance. Chance is this much, as you have seen, and this you do for very small boxes all over the plane, and add the add this. Okay, so you get a weighted sum. Addition is summation now over the entire range, and then divide by the sum of the weights. There is a weighted average, which are called expectation. These are the weights, so you sum them. But this is equal to 1 because this is certainty, probability of certainty, because my range is from minus infinity to infinity, minus infinity to infinity. Capital X comma y falling within this range is always certain. So, probability of that which is given by this double integral, that is the probability of certainty, which is a global phenomenon, a constant, universally constant, that is 1. So, therefore, E is this much. Take the function, instead of capital X y, substitute by small x small y, because they are the integration variables. Multiply by the joint density. So, is a function of this small x small y and dx dy. One thing, expectation, this is called expectation, expected value. Expectation is a linear operation. I will explain what I mean. Suppose consider single variable case, and then we can easily extend to this case also. I will do that. Suppose you are given two functions, f1 x, f2 x. Okay. Now, if you create a function f x as a linear combination of the two, where C1 and C2 are some scalar numbers, real numbers, 2, 3, 4, 5.3, 7.9, anything. Okay. So again, this is a random function, because every time I observe capital X, it is a single variable case I went back to, and can be easily generalized to this also. So every time I observe capital X, this takes a value, this takes a value, so linear combination takes a value. Next time I conduct another experiment, this takes a different value, this takes a different value, these two functions, again the combination takes another value. So this function also random. So therefore, Ex of f of x, capital X here, will be, I have to take this, there is this function f small x and the chance factor, all right. And now if you replace this by this, C1, this is small x, so it becomes small x. Now we know integral is linear. You can separate out the integral into two integral. One is on f1x, so C1 f1x into px dx, one integral. Another is C2 f2x px dx, another integral. So if you do that, you will have C1 times f1x into px dx, which is expected value of f1. By definition, expected value of f1 capital X is what? You replace f1 capital X by f1 small x, multiplied by the chance factor px x dx, integrate, and C1 constant goes out of the integral, plus C2 times, again C2 goes out of integral, f2x and this, which is again Ex of this function f2x. That is why we say linear. Expected value of this is nothing but C1 times expected value of this plus C2 times expected value of this. So expectation from outside can be applied directly on the constituent functions. All right. Expectation of the overall C1 f1x plus C2 f2x will be nothing but C1 times expectation of this and C2 times expectation of this. Same thing we have here. If we have two functions, f(xy) is nothing but C1 f1 x comma y plus C2 f2 x comma y. Okay, here you replace this by that. So one double integral for f1, another for double f2. C1 goes out, C2 goes out, and you get the same thing. So expectation is linear. All right. So this is the average. So now I consider some case. That we already have one random variable x and we know its mean. Okay, that is expected value of x itself. We have done it last class. And y, its expected value is mu y. They are constant, they are not random. Now we are given a function f is x minus mu x, y minus mu y. All right. This is a function x. This function, so what is the expected value? I have to take this double integral, instead of capital X it will be now small x within integral. Again, instead of capital Y inside the integral it will be small y, because those are the integral variables. All right. Sorry, one term is missing. The joint density, most important term, I missed out. All right. This is expected value of this thing. It's a very, very important thing. It is called covariance. I will give you the physical meaning of this. Of x and y, you denote it as C x y. C for covariance. What it means is this, it actually gives you an idea about how well the x and y are related to each other internally. Are they very uncorrelated, no relation between them, or there is some relation, like temperature and humidity has some relation. Okay, but temperature and you see rupee value of dollar, they are absolutely two different things, no connection. So there is no correlation. Both are real, both are continuous. Okay. So you see, x is a random variable, x minus its mean. So what is mean? I am going, this is my mu x, and capital S can be here to here, any fluctuating every time. So suppose it has taken this much value, and again this is your mu y, and y is going like this. So maybe y has taken this much value. So this is that increment, capital X minus mu x in a particular experiment. This is the increment, capital Y minus mu y in a particular experiment. I am multiplying the two, and this product I am averaging. Now suppose x and y are highly related to each other. So when this goes up, either this goes up always, so difference, they are positive, so multiply, you get a positive number, or they go down, it goes down, so it also goes down. So negative, negative, but multiplication is positive. So if they are highly correlated, then what will happen? If this is positive, or this is negative, product is always positive. So average will give a good value. Or it can so happen that the relation is such that when it is going up, relation is such it will go down. So positive increment, negative increment, so multiply, you get a negative value, and when it goes down, it should goes up. Okay, but there is this relation, deterministic kind of thing. If it goes down, it influences this, or this influences this. Either both positive or both negative, or when this is positive, this is negative, and vice versa. When this is positive, this is negative, product is minus, again product is minus, and you average, you get a sizable good negative number. So magnitude of this average will be high. That means if this average is high in magnitude, I will assume that they are influencing each other very well. Okay, so they are correlated. On the other hand, if there is no correlation, as I told you, one is temperature, another is the rupee value of US dollar. No correlation. So it may go up, okay, but while it goes up, it can sometimes go down, sometimes go up. So go up, go down. So positive into positive, and sometimes positive into negative, or sometimes this is negative, this can go up, go down. So again negative into positive, negative into negative. So if you average out 4 cases, it will be 0 or close to 0 if they are not correlated to each other, they are not influencing each other. So if they are uncorrelated, then this value covariance will be 0 or close to 0, ideally 0. So implies x, y uncorrelated. All right, x, y uncorrelated. Anyway, now we come to this formula that was this. Now this I multiply x minus mu x into y minus mu y. Simple multiplication will be x y minus mu x y minus mu y x plus mu x mu y. And I told you is a linear operator. E on summation of these functions is same as E on this, E on this, E on this, E on this, because if you multiply this by the joint density of x y and then integrate the double integral, you can separate out 1 on this, 1 on this, 1 on this, 1 on this. So, you get average of this, average of this, average of this, average of this. So, E x y, x y, this is one term you get, then minus from this minus E x y of this product. Now, here this is a constant, this is not random. So, it will go out, all right, it will go out. Okay. Anyway, I need a small result here. So, once I derive that, then I should come back. So, let me for the time being not pursue this, up to this is fine. I have to go to something called conditional density, and then I will come back to this using linearity, breaking it up in 4 terms and applying E on this, and then trying to see what emerges and all. That is later, one more result I need. So, let me go up to this and then go to the other one, next topic, which is conditional probability density. Let me erase this part. Suppose I am doing the same experiment. We are given two jointly random variables as before. So, this much is my x, this is dx, this is y, and this is dy as before. This point is x y. So, I have to find out the chance of capital X comma y pair falling here. That we have already done. Now, I will do the same thing in another way. Okay. We have already seen probability of capital X lying from x plus dx to x, simultaneously y equivalently meaning capital X y lying here. That we have already seen in terms of the joint probability density, this much. But we can arrive at the same thing in another way. Suppose we first restrict, or rather we first, 1 minute. Restrict the choice of capital X to be here only. So, in my experiments capital X will take any value from here to minus infinity, but I will ignore all others. I will consider only those cases where capital X is from small x to x plus dx. So, we first restrict the choice of capital X, but that will not always happen. That will have a chance factor. That I will bring in later, okay, because capital X as such will take value from minus infinity. Okay, there is nothing that says that that ensures that capital X will be here only always. but I am considering only those experiments in which capital X produces a result from either small x to x plus dx. So, that will have a chance factor, because that will not always happen, that chance factor will bring later. But suppose I am considering only those cases where capital X takes values from either x small x to x plus dx, only those cases. That is, we first restrict the choice of capital X to, all right. Subject to this, now in these cases where capital is fixed here, subject to this, subject to the above, that is capital X is lying here only, then the probability that capital Y will be from here to here, that is from here to here, which will mean capital X comma Y that will lie here, because capital X is lying from small x to x plus dx, and now I am in those cases when it is already guaranteed to lie here only, because I am only considering those cases where capital X lies from small x to x plus dx, only in those cases, again that is keeping that fixed. If I measure capital Y, there is no guarantee capital Y will lie from here to here, or then the pair will lie from will lie on this box, isn't it? So, subject to the above, probability of capital Y lying between y plus dy which is equivalent to x y lying in this box, lying in the box, in the shaded box. That is subject to this, because capital X is already lying from small x to x plus dx, only those cases are considered. Then again capital Y could have been anywhere from minus infinity to infinity. Then I am taking only those cases here, while capital X is fixed here, then subject to that only those cases where capital Y is lying from here to here. Okay. That will again be proportional to dy, because dy is small. So, if dy is large, okay, if dy is large, that probability will go up, chances will go up, or if dy is less, chances will be less. Since dy is infinitely small, I will take this probability to be linearly proportional to dy, and therefore, it is equal to a proportionality constant times dy. Proportionality constant, it is not just a function of y, because capital X also is playing a role. Capital X is taking a value up to small x. Okay. So, it is basically a function of again capital X, I mean where this slot is located, which is small x y. So, we write like this, it is just a notation. Capital Y, instead of writing capital Y comma x, we write capital Y by x. This is a notation, but it actually means it is a function of both the random variables, capital X first and capital Y, and in this order you write small y by x. It means capital X is constrained to take value from small x to x plus dx. X means x plus dx, x to x plus dx. Subject to that capital Y taking value from y to y plus dy. Okay, that is the meaning of this. This is that proportionality constant, that times the width. Okay. So, therefore, or equivalently, because capital X is already lying from here to here, and then under that capital Y lying from here to here, which means under capital X lying from here to here, what is the probability of that pair lying in the box? That is this much. Okay. But as I told you, capital X will not always occur here, only it will occur here only with a chance factor. So, overall chance of this, overall chance of capital X y falling here will be what? This probability times the chance of this happening, capital X lying between small x to x plus dx. So, overall probability of x comma y lying in the shaded box will be what? This chance this actually means it is a function of x and y. But we write like this. We write like this. It means basically capital X takes a value from small x to x plus dx, subject to that capital Y takes a value from y to y plus dy. Then the probability is this, which would mean then capital X comma y will lie here, but under the condition that capital X is only prefixed to take values from here. Only those cases are considered. So, only then the chance is so much, but capital X will not always take value from here. So, overall chance of capital X comma y falling here will be this chance times the chance of capital X occurring here. So, capital X occurring here chance we have already seen in the first lecture, it is so. Now, this and this they are same. This was written in direct way, this is obtained in another way. This is called conditional probability density of y given x. So, these two are same. So, if you now equate, the two, dy dx, dy dx, they are common. So, take them out. So, that means joint density let me write in the next page. This joint density is this into this. That is joint density is y by x if x is constrained to lie between small x to x plus dx, subject to that capital Y lying from small y to y plus dy probability density of that, the next term will be capital X here. If this is the constraint here, then it will be free here, this variable. This is how we get. All right. Now, in the previous page, I constrained capital X to lie from here to here, subject to that I took the cases when capital Y lying from here to here. I can reverse that, interchange that. I can first constrain capital Y to lie from small y to y plus dy, and then see how often capital X lies from this much to this much. So, just same procedure, interchanging capital X and y, capital Y. So, then it will give me equivalently P capital X by y, that is capital O is constraint to take value from small y to y plus dy, subject to that capital X lying from small x to x plus dx. There is the probability that times. Now, this will be free P y y, all right, either way. Okay. Now, if capital X and Y are called statistically independent, or maybe I will do this later, this one not now. I will rather stop here now, because another topic if I begin in 2-3 minutes, it will be, I will not be able to complete that, I will just begin, so it will remain discontinuous. So, we stop here. In the next class, I will build upon this conditional probability series further, some properties and all that. Then I will take up that case of covariance, correlation, and then instead of taking just two random variables, I will then take three, x, y, z, that will show up further properties, and then I will generalize it to n number of random variables together. I will call them x1, x2, capital X1, capital X2, dot, 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 capital Xn. Then will come their correlation matrix, covariance matrix, and all those. Okay, and then their properties. We will go by these. Okay. So thank you very much. If you have any question, you can raise in the forum. Okay, and please follow my lecture here and also the NPTEL video lecture clearly. It will be clear. Okay. Thank you very much. See you then. Bye bye.